All right, guys. Since I had some trouble with the video capture from class yesterday, I'm just going to kind of run through this demonstration again, and that's just a separate video really quick. I think that would be better than trying to fix the problems with the other one. So we talked about last time about how loudspeakers are directional. They don't send the sound equally in all directions, and that is in large part by design. And we learned about some ways to interpret that directivity data and some various graphs. I've got a PDF here of a KF300i, which is a loudspeaker from EAW. And here on the main page, it's got some specifications that are important to us, mainly here where it says horizontal coverage of 90 degrees between 6 dB down points, vertical coverage of 50 degrees between 6 dB down points. So that's what it's specified as, but what frequency is that? Because it's not every frequency. So if we keep kind of like scrolling through here, we will eventually find, okay, here's like a whole bunch of polar plots that they have, and they've got them on octave bands here. So for both vertical and horizontal. So we've got plenty of data to work with here. So let me show you how you could use this data to kind of figure out how the sound would disperse in a room. So here's a CAD drawing of the DeMille Theater on our campus, which is a small proscenium theater that has this weird kind of curved seating area, which presents some challenges. So this is a ground plan and section view drawing of this, and I want to show you kind of how you can use the polar data to decide, hey, how loud will the sound be at each of these different locations, and how you can make that work. Ultimately, this method I'm going to show you is not the method you're going to do it in real life. Nowadays, we would use something like Ease or ArrayCalc or Sound Vision or Map or something like that to plot this for us, and the computer would do a lot of this math for us, which is definitely the way you should do it. But I think it's important for you to understand how those computer programs are coming up with the information that they're showing you. Because if you understand where that information is coming from, then you can understand better how to manipulate it in some of those modeling programs. So that's what I'm going to show you kind of on a very small scale what those computer programs are doing when they plot these beautiful coverage plots. So what I've done is I've gone and I've made some marks on this space. So this point here is where I'm going to hang my KF300. And in this space, this is what we actually are using. We're using a KF300s in here. So we have the center hung here. And I have marked some seats here. So I have seat A, B, C, D, which are on the center line. And then over here, I've got E, F, G. And then over here, I've got H and I. Now, I very specifically chose these spots. This line, if I measure this line, the angle between here and here, you'll see that it's a 45-degree angle. And that's very important because the manufacturer says that this loudspeaker has a horizontal dispersion of 90 degrees, which would be 45 degrees on either side of center, and that's where you hit 6 dB down. So I'm going to plot some spots there. And normally I would only do 3 rows, a front, middle, back, but because the back row on the center line ends here, there really is no 45-degree seat for that back row seat. I've instead gone and picked up this spot here, which is probably the new back row at that 45-degree angle. And therefore, I'll plot on axis at the center line for that row as well. And then these two over here, H and I, there's not a particular rhyme or reason to this that has anything to do with the loudspeaker. It's just that this is kind of about what I would imagine the limits of the seating area to be. I don't think they're going to seat people right here close to the stage. They might seat a couple of people here. So we'll see. If we think it's going to be a full house, we might want to take a look at that. But I figure like this is a good spot to just sort of see what the edges are in the coverage. So those are the spots I'm going to do. Now what I've done is I've created some construction lines from those spots down here to the section view where I also have A, B, C, D. And obviously I don't have the other ones because they're not on the center line. And I've also dropped that same construction line down here for the center cluster in the section view. All right. So now I know where I'm going to plot everything. So let me now show you what I've got set up here to keep track of this information. So I have in Excel a bunch of columns set up here, A through I. And I want to first find out how far away each of those seats are from the loudspeaker. And there's a couple different ways I'm going to have to do that I'll explain as we go here. And once I have those distance values, I can use that to calculate the dB loss over distance. And you'll see here that I've got a formula in here that's just basically 20 times the log of 3.28 feet divided by whatever the distance is it's away. And the 3.28 feet corresponds to 1 meter, and we have specifications for what the loudspeaker can do at 1 meter, and therefore we could use that data to figure out how loud things are going to be. So that will just tell me how much I'm losing traveling through the air to that spot. Now, I also want to figure out how much I'm losing vertically and horizontally as a result of directivity. I'm going to figure that out by recording the angles off axis, vertically and horizontally, at each of these seats from the loudspeaker. And then I will enter the dB loss that I get as a result of directivity there. And then I've got some equations here that will calculate the total loss. So for example, here I'm doing the loss over distance plus the vertical loss plus the horizontal loss. And that will get me the total dB loss at that seat. And then this one here, which I'm calling difference from axis, is really just how much different is this spot from whatever spot the loudspeaker is pointed at, the on-axis point, which in this case is seat D, which is the back row center. So I'm just comparing everything against that, and I'll get a range here that shows me, you know, the range of difference I have across the seating area. Okay, so let's just start doing this. So the first thing I want to do is get these distances. So I'll start with these seats that are on the center line. And zoom a little bit more. Okay, so I'm going to measure these distances. So seat A is 22.351. That's the distance, okay? Seat B, it looks like, is 27.3884. Seat C is 33.6442. Seat D is 38.7703. Okay, so I put those in, and I'm automatically calculating dB loss over distance. Now, it's just important to kind of check your math here and see that seat C is only 22 feet away, and seat D is 38, almost 39 feet away. And so you would expect seat D to be quieter. You will have lost more as a result of traveling farther, and that does seem to track. As we get farther away, we are losing more dB, which we're ranging from 16.5 dB loss to 21.5 dB loss. So, okay, that's great. Well, let's take a look at these other seats now. Here's the problem. I have these seats over here on the ground plan, but figuring out the distance that these are away from the loudspeaker is not as simple as just measuring from point to point here, because that doesn't account for the vertical drop. So to figure out the location of these seats, you have to do Pythagorean theorem. And the Pythagorean theorem, as I understand it, says that in a triangle, the of three sides that you could call side A, side B, side C, the length of side C is going to be equal to the length of side A squared plus the length of side B squared, and that sum will be the length of C squared. So A squared plus B squared equals C squared, which if you want to find out what C is, C would equal the square root of A squared plus B squared. Okay, so I have created in my spreadsheet here an A distance and a B distance. And I can get those two values from the ground plan to the center and the section view. And then here for the actual distance, I'm doing the square root of A squared plus B squared. Okay, so let's go ahead and get that. So over here, I can get, if I measure, and I'll make sure I get the exact right thing here. So seat E is 15.4252. So I'll put that in for A. And then I'll try again for seat F, and that is 25.0229. Okay, G is there, 34.7437. Okay, and then we'll get H, which is 18.7827. And I is going to be $29.1694. Yeah. Okay. All right, so those are the A sides. Now, if I go to the section view, I can get the B sides. So what I've done is I've drawn lines from these points in the section and connected them perpendicularly to the construction line that that tracks with the vertical of the center loudspeaker. So the side I'm looking for here for these front row seats is going to be measured from this point to this point. I got 17.75. Okay, so that would go 17.75 in for E, and then I believe it's H that's also on the front row. Let me just double check. Yeah, H is also on the front row, so it's also going to get 17.75. Okay, and then let's go get the one for the second row here. Let's see, it's going to be here to here, 22.7499. And this will also get that, 22.7499, seat I, because that's on the same row. Okay, now we'll do seat C, 31.7807, which will go in for G. Yeah. Okay, so it's done the math and it's figured out the actual distances. And from there, it has calculated dB loss. And here's my total loss so far per seat. And it's calculated the difference between them. So the biggest number right now is this, the 4.78 dB. That's a positive. And then I go all the way down. The lowest value is negative 1.7. So, we're within 6 dB, but we haven't accounted for directivity yet. So let's plug in some angles now. Let's assume that we are aiming at the back row, which is what professionals tend to do. So I want to measure the angle between seat D and seat C, and that is 8 degrees. So the vertical angle is 8. Actually, I'm going to say -8 because I'm going down for that. The vertical angle, actually, that'll be on C. Won't it be? Okay. D is going to be 0 because that's where the loudspeaker's aims. There's no vertical loss there. Let's look at the angle from D to B. Okay, that's 23 degrees, so I'll put -23 in there. And let's go to seat A. Here to here, 41 degrees. Okay. Now, we can take this information and we can get these angles. This will be -41. We can put these over here as well. So -41 would also go here for seat E. Right, because it's also on the front row, so we would get the same vertical angle. F would be the -23, and G would be the -8. H is also on the front row, so it gets the -41, and I gets the -23 for vertical angle, because it would still be the same. Horizontal angle, we'll have to get from the ground plan. So we know, we already measured that E, F, and G are 45 degrees, right? Because we looked at that already. So let's go ahead and put that in. Horizontal angle is 0 for A, B, C, and D because they're on the center line. But E is going to be 45 degrees. F is going to be 45 degrees. G is going to be 45 degrees. So let's measure the angle between the center line and that line. Okay, that's 74 degrees. So we'll do 74 here, 74 there. Okay, so now I just got to go consult these polar plots. So let's start with the vertical. If I look at the vertical polar plots here, I've got to pick a frequency. Now, if you were really doing this, you would want to figure this out for multiple frequencies, but just for purposes of demonstration, I'm just going to do one frequency. It doesn't look like here that at 1 kilohertz the directivity is really kicked in much. At 2 kilohertz it's definitely kicking in, but it's a little asymmetrical. But once I get to 4 kilohertz, now this thing this looks pretty controlled. So I'm going to just do this at 4 kilohertz because I think we'll get reasonable data from there that we can make decisions on. So 41 degrees off axis vertically. You kind of have to estimate here. So this is 30, this is 60, which means 40 would be here, 50 would be here. So 41 is about here, which is 6 dB quieter, maybe 7. Yeah, I'm going to say 7. So the vertical loss here is -7. Okay. Now -23, so 10 is here, 20 is here, so 23. It looks like we're maybe 3, maybe 4 dB. Let's say -3. Okay, -8 degrees, that would be about here. We've maybe lost 1 dB. So put 1 there. No vertical loss at seat D because we're not off axis vertically. Okay, now seat E has the same vertical angle, so we'll do a -7 there. We'll do the -3 there because that's also the 23 degrees, and we'll do the -1 here. This will get a -7, and this will get a -3 because they got the same vertical angle and therefore the same vertical loss. Now, as a side note, in real life, these wouldn't be a perfect summation of the vertical and horizontal loss because the dispersion is probably somewhat conical, but we don't have that information in polar plots. We just have horizontal and vertical. And when you have something like ease or any of the other options that are out there, it has that data that is multiple angles besides just horizontal and vertical. But for this purpose, to keep it simple, we're just going to sum the vertical loss and horizontal loss. And in the back of our mind, we will know that it won't be quite that bad at those extreme off-angle points. So, okay, horizontal loss is going to be 0 for these seats because they're on center line, so they haven't gone off axis. Seat E is 45 degrees, so let's go up here to the horizontal polar plot at 4 kilohertz, and 45 degrees. Well, 50, that would be halfway through here, and oh look, it's exactly 6 dB, just like they said it would be. So there you go, 60 minus 6, minus 6, minus 6. So that spec for that 90 degree horizontal, 6 dB down points that they said, that's at 4 kilohertz. Okay, then we need to go 74 degrees. Well, there's 60. 70, 80, 90, so 74 is about here. We're probably about 12 dB down there. So we'll do 12 here and minus 12 there. Okay, we did it. Now let's look at the difference. We have, the loudest thing we have is 0, or actually this is just fractionally, but you would never hear the difference. That's functionally 0. That is 2. So 0 dB is the loudest and minus 15 is the quietest. So I have a 15 dB range here, which is not cool. I mean, we want it to be within 6 dB. So here's what we would do to fix this problem. What I want to do is I'm going to need 2 of these. And if we look around here in the manual, we will see they have this flybar that you can purchase or build. And oops, what it does is it allows you to put a SB330 sub here in the middle and then a KF300 on either side. And they're angled 45 degrees off axis to either side. So they're doing that. Now what that does is we know that this loudspeaker is, generally speaking, 6 dB quieter when you go 45 degrees to either side. So what will happen here is when you mount it in this bracket, this will space them just so in the way that when you hit this center point, that will be the 6 dB down point for both loudspeakers, and they will be perfectly lined up. You would have to get them perfectly lined up in phase, and then you would get a 6 dB boost because they're perfectly coherent, and therefore everything between the on-axis here and the on-axis here would be considered on-axis response because the directivity loss is being compensated for here as a result of the overlap, and it's an overlap that doesn't cause destructive comb filtering for the most part. There will be a little bit of a dip right over on this side of the center line and a little bit of a dip right here, just very small. But other than that, it'll be pretty smooth. So this is what's called a horizontal point source array. And you do that by splaying them, trying to line up the 6 dB down points in the middle, and then it sums together. So now what we're going to do is we are going to take this thing and we are going to aim it to seat G. Okay, which then means that these A, B, C, and D will be the off axis. That'll be the 6 dB down point. So let's take a look here and see what we've got to do. So if we are aiming at seat G, first thing I want you to notice is I've altered my formula here, my difference from axis formula, to be seat G. Okay, that's what it's comparing against. Well, okay, the distance data is going to be all the same. Okay, those seats are still the same distance away in our hypothetical world here. In reality, obviously, you're going to scoot them 1 foot or 2 in the other direction, which will tweak the distances ever so slightly, but it's probably not enough to make a significant difference in the dB loss. So I can just copy that data down. Now I've got to think about the angles a little bit. So the vertical angles here are still going to be the same for A, B, C, and D. So it's still minus 41, minus 23, minus 8. Actually, but now I'm going to be aiming down, aren't I? So I'm going to be aiming at G, which is that row of C. So actually C is going to be, these all will be different. So let me go get those different values. So measure angle, let's go from between there and there is 8 degrees. Okay, so to seat D, it's going to be 8 degrees on the vertical. This will be 0. And then from here, I'm going to go from C to B, and that's 15 degrees, minus 15. And let's measure from seat C to seat A. That is minus 33 degrees. Okay, so there's my vertical angles there. Now horizontally, I know it's going to be 45 degrees. Okay, because we've rotated it by that much. Now at this point, F, G, and H are, or it's not F, G, and H, E, F, and G are going to be 0 degrees horizontal because that's the axis. And their vertical loss will be the same as these. So F is going to be the minus 33, G will be the minus 15, or F. I have to keep looking at the column headers. I need to look here. So E is minus 33, F is minus 15, because those are on the same rows as A and B. And G is going to be 0, and H is going to be minus 33, I is going to be minus 15. So we just got to figure out the horizontal angles now for seats H and I. So let's come over here and measure this angle. So between here and here, I get 29 degrees. So this will be 29. Okay. So now I can go figure this out. So if I go back to this, let's go and get the vertical data at 4 kilohertz again. And I'm first looking for a vertical angle of negative 33 degrees, which there's 30, 33 would be about there. Okay, we haven't quite hit 6 dB down. We're probably at minus 5, okay? So this will be minus 5 for vertical loss there. Okay, minus 15 degrees is here, and that looks like it's maybe minus 2. D is 0, so that'll be 0 vertical. Over here, I want to go to the other side because now I'm 8 on this side, which, again, maybe we've done 1 dB, so minus 1. Now, the horizontal loss here is 45 degrees, which is about here, which is the 6 dB down point, okay? So, well, actually, isn't that interesting? If we go 30, 45, on that side, it's a little bit lopsided, but over here, oh, sorry, I'm looking at the vertical. I'm like, why is this not making sense? Let's go look at the horizontal. Okay, yes, okay, so here we go to 45 degrees and there's 6 dB down. So I was very confused for a moment there. I was expecting it to be 6 and it wasn't, but I was looking at the wrong plot. Okay, so these will be minus 6, we know that, okay? Now, vertical loss here is going to be minus 5 for this one because it's the same vertical angle. This will be -2. This will be 0. This will be -5, and this will be -2. And no horizontal loss at these 3 seats, because that's where the loudspeaker is pointed. And I just now need a horizontal angle of 29 degrees, which is almost 30, which looks like it's about -2, maybe -3. Yeah, -2. So -2, -2. There's a lot of wiggle room here. I mean, all of these are probably give or take a dB, but it's going to be close enough. Okay, so here's the interesting thing. All these -6s, that is true if I have one loudspeaker. So if I have one loudspeaker and I do point it over to the side, then yes, over here in the center line it would be -6. But in reality, I'm going to take another loudspeaker. So I'm going to have a second one over here that's pointed this direction. And therefore, its 6 dB down point will also hit the center line, and they will sum together if we can get them perfectly lined up. And that becomes 0. So I can effectively just put 0 in here, assuming I'm using two that are arrayed 90 degrees between their axes. Which means if I set those to 0, then at this point, our differences here are the loudest thing is about 3 dB and then -2. So that's a range of 5 dB. I've done it. I'm within 6 dB. Okay? So it works. Effectively, what has happened here is everything between this line and this line will behave as though it is in on-axis horizontal response, okay? So it's going to be just like that loudspeaker is pointed at all the seats in here on-axis horizontally. So all you're really taking is the vertical loss there. And then the only real horizontal loss you start incurring is when you get outside of this. So we've effectively taken a loudspeaker that was a 90-degree horizontal dispersion between 6 dB down points, and we've turned it into a new loudspeaker that's in reality a cluster that together do 180 degrees between 6 dB down points on the horizontal, which definitely covers this area. And that is how it works. Again, I'm not saying this is the way you should do it if you're really trying to design your sound system. I'm just saying that this shows you how this information is, where it comes from when you're using a program like Ease or ArrayCalc or Map or SoundVision or Lara or any of these other ones that you might use to plot your loudspeaker coverage. This is more or less what those programs are doing when they give you all those beautiful pictures that have colors corresponding to loudness. They're doing this kind of calculation. The difference is they have much more data to work with about the directivity of the loudspeaker. They've got multiple axes that it can consider, and we only have horizontal and vertical, so there's some limitations when you do it manually like this. But this is how they do it. Okay, so hopefully this is a good enough reminder for you on the homework this weekend, and you will do a version of this for the spaces that are on Canvas. So good luck.